Hello everyone, I'm Qingzhao Zhang, a PhD student from University of Michigan, and today I'll introduce the work, a systematic framework to identify the violations of scenario-dependent driving rules in autonomous vehicle software. So first, I'll briefly talk about the background information, the emerging level 5 autonomous vehicles, AV for short. This kind of AVs have full driving automation. It means no human attention is required to drive the vehicle. However, related applications or systems are still under active development and they are not yet available for the public. But one concern is that if the AVs are available, they will share the roles with human drivers, and for the safety concerns, AVs need to obey the same driving rules as human drivers do. Then we are interested in what driving rules should AVs obey. Basically, there are two types of rules. The first type is the general safety considerations, like avoid any collisions. This kind of rules should be satisfied all the time as long as the vehicle is on the road and are already implemented by most AV software. However, the second type is the rules for specific scenarios, like crosswalk, intersection, stop sign rules, or we can call them scenario-dependent rules. The vehicle's behavior then depends on the surrounding situation, which sometimes is a complicated logic. However, for now, we cannot see any standard for AV software development about its rules, especially the more complex scenario-dependent rules. So one straightforward question is that, did AVs correctly implement these driving rules? Then we surveyed the implementation of open source AV software, including Apollo and AutoWare. AV is a quite complicated computing system, and the general software pipeline looks like this. First, AV accepts data from sensors, including cameras, LiDAR, and radar. Then the perception module processes the data and gets knowledge of the surrounding environment. Based on the perception, planning module decides the AV's behavior, for example, take brake or decelerate. The decisions of planning module then will be passed into the control module, which is a cyber-physical module controlling the physical car. Especially the driving rule implementation is part of the planning module, which is reasonable because handling driving rules is also about making right decisions. In this work, we focus on the planning module. We then look at two software, Apollo and AutoWare, in depth, and we found some general problems in their driving rule implementation. So first, their implementation has incomplete parts. There are to-do items in their source code. Also, the implementation may be buggy, and there are bug-fixing commits in the repos. Given the problems, here comes our research question. How can we validate the driving rule implementation in AV software? Especially the validation of scenario-dependent rules is more challenging because their logic can be complicated. And then we found that existing AV testing approaches have limitations for this specific goal. First, unit tests and fuzzing. These conventional software testing methods can reveal low-level code errors, but not rule-level, high-level logic errors. Track testing and road testing is the most realistic way of testing AVs, but very expensive in terms of the regulations and physical challenges. And simulation-based testing, on the other hand, makes the trade-off between accuracy and efficiency. We can see the above approaches can complement each other in some ways, but all above approaches have common limitations. First, they all rely on a large quantity and a variety of test cases to cover the edge cases, which is quite difficult because the traffic scenarios can be complicated and infinite. Second, the testing completeness cannot be guaranteed since we can never enumerate all the possible scenarios. Third, they do not check the scenario-dependent rules. To close this gap, we propose to build a general testing framework for AV developers to validate driving rule compliance in AV software using the formal methods. The key idea is that we can formally represent the whole problem in symbolic variables, including the traffic scenes, AV behaviors, and the rules. And then we can use the formal methods to directly inspect errors in the logic instead of randomly trying numerous test cases. And let's see the figure below, which summarizes the workflow of our framework. First, we translate the AV code, maybe in the high-level programming languages like C++, into our proposed formal specification called behavior spec here. This process is assisted by developers' annotations and automated by a program analysis pipeline, which is the semantic analysis block in this figure. Also, someone with expertise on the driving rules should write the specifications of driving rules. Then we do an SMT-based verification to review inconsistency between the two specs. The full name of SMT is the Satisfiability Modulo Series, and the SMT solver is a tool solving constraint satisfaction problems. The solver can tell us whether the violation exists, and if there is a violation, it produces one example, which is the violation case. And finally, we transform the violation case to a simulation case and use simulators to double check the violation. We can see that the whole detection process is static without the need of random fuzzing. Also, the formal verification process can provide the guarantee on testing completeness. The key contributions here include: first, we designed a symbolic representation for this domain, and based on this representation, we can write the AV's behavior spec and rule spec, which enables the subsequent formal analysis. Second, we build the framework by integrating a set of techniques and make the framework usable. The framework is also general because it can support different AV software and the driving rules. Next, I'll talk about more details of the framework by showing one running example, the stopping at crosswalk example. So the driving rule from US Department is simply described in the natural language. Stop at the crosswalk when there are pedestrians using it. While Baidu Apollo is executed in cycles, and each cycle it makes decisions according to the road situation. Then let's see the first step, writing the specifications. So the figure below shows the format. For the code side, we use a state machine to represent the code logic. And the software contains the software state, and the actions are made conditionally from specific states. In this example, we can see the AV may stop when there's a crosswalk ahead. The rule specification, on the other hand, has two main components, action and the condition. It is quite straightforward that the rule requires the driver to take an action while the condition is met. Interestingly, the action and the condition are common things in two specs. We can define actions as a finite set, but a condition is not trivial to represent since it may contain complicated logic, including the geometric information and temporal information. As a result, I'll introduce more about the condition. We propose to use the traffic snapshots to represent its conditions. Basically, our approach is to use symbolic variables to describe the traffic scenario on one moment, and then use a constraint on the symbolic variables as the condition. For the geometric information, we draw on-road objects into a two-dimensional space under the SL coordination system, where AV is in the center, the x-axis is along the road, and the l-axis is the lateral distance. As shown in the right side, cars, pedestrians, and crosswalks all become shapes in the 2D space. And geometric information, for example, the crosswalk is the head of AV becomes the relationship between two rectangles. For temporal information, for example, how long has the vehicle stopped? We add new symbolic variables as properties of the vehicle object. The representation is extensible if there are more tricky information we need to handle. And this snapshot representation is simple but sufficient. We do a few abstractions like from objects to shapes and split the continuous time into moments into snapshots. But however, we sufficiently support the main information in the driving rules, including geometric information and temporal information. So we use the above ways to represent actions or conditions. And then we have these specs for the running example. To alleviate the manual effort, we design a set of user interfaces and APIs. For example, approach defines that object A is moving towards object B. And the geometric relationship includes in, on, cross, etc. However, the AV's behavior spec is still complicated due to its state machine structure. So that is why we applied program analysis to automate this process. And the program analysis pipeline looks like this. The input is the source code of AV software, and we compile it into LVM AR, intermediate representation, so that our method can be general for different front-end programming languages. And the next step is important, which extracts the code logic from LVM code, but drops the low-level details. Otherwise, the high-level driving rules cannot match the low-level AV code. This is done mainly through the predefined lookup tables. For example, the LVM operators add, multiply can be mapped into corresponding SMT operators. And structures like vector in C++ also can be mapped into arrays in SMT. More than that, we need assistance from developers to annotate complicated APIs. For example, isPointIn API means the geometric information in, and build stop decision, the function means the action stop. After the code is cleaned and only contains the pure logic, the symbolic execution is applied to extract the path constraints. The path constraints indicates when the software will shift the state or take actions. And the constraints are already the SMT encoded conditions, and we can directly insert them into the spec. So this is how the program analysis pipeline extracts the spec from AV code. Okay, then we have the specs already. In this figure, the conditions are no more natural language, but formal representations we define. Now we are going to write the violation constraint. If the traffic snapshot satisfies the violation constraint, the AV is possible to break the driving rule. So when the violation may happen, first, it should satisfy the basic physical constraints, or we call them basic snapshot constraints. For example, the shape and velocity of all objects have limits. Then it should satisfy the condition in the rule spec. Otherwise, the situation is out of the scope of the driving rule. Then the AV's behavior should be different from the rule. In this case, the AV requires the AV to stop. So we need the constraint for the AV to stop and take the negation. So that is what we want. So first, state start is reachable, and then action stop is taken from start. And combine them together, we have the constraint for AV to stop, and we take the negation. So finally, the SMT solver looks for the solutions for the violation constraint. If there's a solution, the violation exists, and that solution is actually the counterexample of the driving rule. So last step is the violations rule simulation. Here we can see the counterexample on the left-hand side is translated to the simulator case on the right-hand side, and they look very similar. Then the simulation will try to reproduce the violation in a more realistic setting. And we did find a violation on this very simple crosswalk rule. The behavior of Apollo is a bit aggressive, since it tries to avoid collisions only, but does not yield to the pedestrians. So if you stand still and or move very slowly on a crosswalk, the AV will not decelerate. And this behavior may cause accidents, even collisions in the real world. Not only the running crosswalk example, we tested our prototype on 2 AV software, Apollo and AutoWare, with 28 driving rules, and we found 15 violations in total in scenarios including crosswalk, stop signs, intersections, traffic light, etc. And there are 2 main causes of the violations. 5 violations are because of the incomplete implementation. Some special and unusual scenarios are just not considered by the software. The other 10 violations are caused by improper predicates. Just like the running example, the condition for the AV to stop is inconsistent with the rule. And more test cases studies are in our full paper. For accuracy, our framework is still not an end-to-end zero false negative verification framework, since the annotations, code analysis, and the simulation are all possible sources of some minor inaccuracy. And what we did is to reveal violations in an effective way to our best efforts. And the framework has a similar false positive rate with the simulation-based methods because we also use the simulation as the final validation step. And the zero false negative guarantee works under the assumption that the specs are sound. So we require the developers to manually double check the specifications. For efficiency, the code analysis take around 25 minutes on either Apollo and AutoWare, and the SMT solving process itself takes only around 10 seconds. For many effort, the preparation of AV code and driving rules is isolated, which means that changing the driving rules does not need to modify anything about the AV code, and vice versa. So set up the AV code needs around 4 man-hours, mainly for the annotations, and writing the rule specifications takes a few minutes. Finally, we got some insights from this work. In terms of the testing framework design, we think that the formal methods can improve the testing efficiency on specific modules in AV systems if that part has some predefined standards or rules. Also, we think our approach can be generalized on more AV modules or robotic systems. For AV development, 2 parts can be improved. First, driving rules in natural language are too vague to be directly used for safety checking. It is better to have AV-specific driving rules. Second, the software development can be improved to consider the compatibility with the formal safety checking, which can make the formal checking simpler. That's all for my presentation. Thank you for listening.